In the next 3 videos, we will look at the 8th topic in deep learning, weights initialization. The weights are typically randomly drawn from a normal distribution with zero mean and sigma squared variance, or from a uniform distribution. The size of the weight variance affects the performance of a neural network. Finding the optimal weight variance size is the subject of this series. In this series, we will look at the method proposed by Xavier Glorot and the method proposed by Kaiming He. This video is part 1, and we will observe how the distribution of output values changes depending on the initial weights of a hidden layer. This video was produced in Korean and translated into English. My voice is AI-generated, text-to-speech. Let's take a look at the full table of contents. In the first video, we'll go over what you need to know before we dive into how to set weights effectively. We'll look at the parameter space and errors, and see how the distribution of hidden layer output values changes depending on the initial weights. And we will derive a formula to calculate the variance of the hidden layer output. This formula will be used in the next 2 videos. In the second video, we will look at the weights initialization method proposed by Xavier Glorot. First, let's look at how to initialize the weights with a normal distribution. We will look at how to find the optimal variance for the weight distribution via forward and backward propagation. We will use the average of these values as the optimal variance for weight initialization. And we'll also look at how to initialize the weights with a uniform distribution. Finally, let's look at Xavier Glorot's initialization method using Keras. In the third video, we'll look at the weight initialization method proposed by Kaiming He. As we did in the second video, we'll look at how to find the optimal variance through forward and backward propagation for normal and uniform distributions. And let's look at Kaiming He's weights initialization method using Keras. Now let's think about the parameter space of a neural network. Properly setting the number and initial values of parameters is a critical step in training a neural network. Since we don't know where the true values y are, we don't know how wide or deep to build a model. The number of parameters w is determined by the width and depth of a model. Models with a small number of parameters may have large errors and underfitting, while models with a large number of parameters may have small errors but overfitting. In this simple model, there are 2 w's, so we can think of a 2-dimensional parameter space like this. And let's say the true value y is somewhere around here. We don't know where it exists or even in what dimensional space it exists. This model learns the true value y using only 2 parameters, w1 and w2. Training a neural network means finding the optimal parameters, w star. Let's assume that the initial values of w's are at this point. During training, w1 and w2 are continuously updated to reach the optimal point. Since the parameter space is 2D, w1 and w2 will move to the point where the true value is projected into the 2D space. This model uses w star at this point to predict y hat like this. This is the best we can do to predict the true value with this model. Then we get this much error. This is a fundamental error that cannot be reduced any further in this model. If there's a local minimum at this point, and if w falls into this point, then this much error is added. And the overall error increases by this much. And this path varies depending on the optimizer, such as RMSprop, Atom, etc. If the initial values of W are at this point, this model will try to find the optimal point through other paths, for example, this path. Since this model has 9 W's, we can think of a 9-dimensional parameter space. This model is slightly wider and deeper than the one on the left. As on the left, the 9 W's will move to this point, where the true value y is projected into the 9-dimensional space. This is the y-hat predicted by this model. In general, the error of this model can be smaller than that of the left model. However, because it is a multidimensional space, there may be more local minima and overfitting may occur. For this reason, it is not easy to determine the appropriate number of parameters for a model, i.e., the appropriate width and depth of the model. Additionally, the initial values of parameters also affect the performance of models. Depending on the initial values, vanishing or exploding gradients problems may occur, and local minimum problems may also increase. The performance of the model may differ if the initial point of W is here or here. Therefore, it is necessary to set the initial values of W appropriately. This is the main topic of this series, weights initialization. In general, models that are sufficiently wide or deep perform better. If they are prevented from overfitting by regularization or dropout, and if the initial weights are set appropriately. Next, let's observe the distribution of hidden layer output according to the initial weights. We have a neural network model like the one shown on the left. There is an input layer with 100 neurons. And there are 2 hidden layers, each with 100 neurons. And there is an output layer. We used linear activation functions for each layer. Near the origin, sigmoid or hyperbolic tangent can be assumed to be linear. The distribution of the input data x is a normal distribution with mean 0 and variance 1. And the distribution of the initial weights in the hidden layer is a normal distribution with mean 0 and variance sigma squared. The output of the first hidden layer is S1, and the output of the second hidden layer is S2. Let's observe the distribution of outputs of these hidden layers as the sigma of initial W changes. The distribution of a hidden layer output values changes depending on the initial values of W. We initialize this neural network, but we do not train it. We fed data X into this neural network and observed the distribution of S1 and S2, which are the outputs of these hidden layers. When sigma of W is set to 1.0, the distributions of S1 and S2 are as follows. The distribution of S1 is like this, and the sigma is 9.461. The distribution of S2 is like this, and the sigma is 98.865. The two distributions are quite different. This is not good. Our goal is to keep the variances consistent across all layers so that the same information can flow through the network. This helps prevent the gradient from vanishing or exploding. If we set the sigma of W to 0.3, the distributions of S1 and S2 are as follows. The difference in variance is greatly reduced, but the sigma of S2 is still about 3 times larger. If we set the sigma of W to 0.15, the distributions of S1 and S2 are as follows. The difference in variance is further reduced. If we set the sigma of W to 0.1, the distributions of S1 and S2 are as follows. The two variances are very similar. Let's lower the sigma of W further. As the sigma of W decreases to 0.05, the difference between the two variances increases again. The sigma of S1 is about twice as large as that of S2. If we lower the sigma of W to 0.01, the sigma of S1 becomes about 9 times larger than that of S2. Then we can see that it is best to set the sigma of W to 0.1. That is, it is best to initialize W using this distribution. This is the basic idea of weight initialization. The mathematical method of finding the optimal sigma value will be covered in detail in the next video. This can be found using the methods proposed by Xavier Glorot and Kaiming He, respectively. Next, let's look at the code that observes these distributions. Let's create and initialize a neural network like this, and then observe the distribution of outputs S1 and S2 when data X is input. We import Keras initializers to initialize the parameters, generate a simple dataset with 1,000 data points. They are random samples from a normal distribution with mean 0 and variance 1. We will create a neural network with 2 hidden layers. This neural network will only be initialized and not trained, so there is no output layer. The weights in each hidden layer are initialized with a normal distribution with 0 mean and sigma squared variance. The number of neurons in the input layer is 100. The number of neurons in the hidden layer is also 100. The weights are all 100 matrices. The outputs of the hidden layer are S1 and S2. When 1,000 data points are fed into this model, both S1 and S2 will be 1,000 by 100 matrices. Let's create a model by changing sigma like this and observe the distribution of S1 and S2. We use the Keras initializers to sample the initial values of W from this distribution. Create an input layer and add 2 hidden layers. We initialize the weights of these hidden layers to W0. Create a model that receives data X and outputs S1. And we create another model that takes data X as input and outputs S2. If we feed data X into these models, we will get S1 and S2. Let's observe the distribution for the first column of S1 and S2. Finally, we plot the histograms of S1 and S2. Let's run this code. The results are as follows. Next, let's create a formula to mathematically calculate the variance of the outputs of a hidden layer. We want to find the variance of this output. Here, the subscript of S represents the output of each neuron. This formula will be used in the Xavier Glorot and Kaiming He methods covered in the next 2 videos. I referred to the documents below. There is a neural network like this. This is an upper layer with K neurons. This is a lower layer with N neurons. We want to create a formula to find the variance of S, the output of the upper layer. Assume that the expected value of W and the expected value of Z are both 0. The matrix S is calculated like this. S is the dot product of Z and W plus B. Z is M by N matrix. M is the batch size of input data. The W is M by K matrix. And biases are added here. Then the matrix S can be expressed as follows. S is a M by K matrix. The variance of each column in this matrix S can be expressed as follows. This term is for the case where J is 1, and this term is for the case where J is 2. This term is for the case where J is N. The bias is a constant, where Zi refers to entire row from 1 to M. And we assume that S, Z, and W are all independent and identically distributed random variables. Then the variances of these terms are all the same. Many assumptions are made here to simplify the mathematical model. Then, the variance of the first column of matrix S can be written as follows. Since S is IID, the variance of SI can be said to be equal to the overall variance of matrix S. For the same reason, Zi and Wi can also be written as matrices Z and W. Therefore, the variance of S becomes as follows. N is the number of neurons in the lower layer. This formula will be used in the Xavier Glorot and Kaiming He methods covered in the next 2 videos. So far, we've looked at the basics for understanding weight initialization. In the next video, we'll look at the weight initialization method proposed by Xavier Glorot.